everybody. This is our final project for the mechanism sessional course. We've done our project on a windscreen wiper mechanism. The members of the team include Hassan Akhtar, Jaivir Simdodia, and me, Athar Ganju. So the basic flow of our presentation will be first we'll explain the problem statement, then some relevant aspects of the theory that were used by us through the course of our project. We'll do a pen and paper synthesis of this problem, followed by calculating the area that is swept by the wiper and the degree of freedom of the mechanism. Then we'll use an analytical analysis to come up with a rough formula for our code to link the input and output angles of our mechanism. Then we will do a MATLAB simulation of our mechanism, followed by some adjustments that can be used to tweak parameters such as the area swept by the wiper or the torque that the wiper experiences. After that, we consider some real life considerations of a wind wiper mechanism in terms of the torque requirements and increasing the efficiency through alternative wiper systems. So this is the problem statement. This is a direct snippet from tutorial 2, problem 6 that is used to formulate our wind wiper mechanism. So the theory behind the mechanism essentially hinges around the Grashof law. So the Grashof law states that the combined length of the shortest and the longest links should be lesser than or equal to the combined length of the remaining two links if the shortest link is to be capable of unrestricted rotation. Uh, for this particular mechanism, this is a Grashofian chain as the minimum link length is about 30 millimeters, the longest link length is about 200 millimeters, and through basic geometric processes, we've calculated the other two links to be about 80 millimeters and 158 millimeters. Doing the required calculations, we find that this is a Grashof chain. Then this is a diagram. This is a direct picture from tutorial 2, question 6, where we've done a pen and paper synthesis of this situation. Then to calculate the area, we've considered an angle swept of about 90 degrees, as that is what was convenient to us in our MATLAB simulation. Calculating the area swept, we find it to be about 942 centimeters square. Then the degree of freedom has been calculated through the standard formula that was used in our kinematics of machines course. We found it to be around 1 for this system. So the formula used for our code essentially comes from the analytical analysis of this mechanism, where we've applied the loop equation to link the input and output angles. Through the loop equation, we have equated the real and imaginary parts to uh, essentially find a link between theta 3 and theta 4. We've gone ahead and used some mathematical operations to come up with a final result, which is on the screen right now. That has been used in our code to link the input and output angles.
Hi, I am Hassan and I will be going through the simulation and code part of our project which we have written in MATLAB. This is the entire code and it basically builds and simulates a full 4-bar mechanism which is windscreen wiper. The first thing I do is define all the fixed pivots and link lengths O2, O4, O6 and all the link distances. This is the geometry of the actual wiper mechanism, so the entire motion depends on these parameters. Next, we pre-allocate arrays for all the link angles and joint coordinates. This is just for speed because MATLAB hates when you grow arrays inside loops, so we size everything up front. I also initialize trace arrays for the two ends of the wiper blade because later I'll use them to show the wiped area. Then this loop is the core kinematics. For each value of the input crank angle theta 2, I solve the loop closure equation to get the other link angles theta 3 and theta 4. Using these computed theta 3 and theta 4, we compute the positions of every joint A, B, C, and D, and finally the two ends of the wiper blade. This loop is doing the actual mechanism motion frame by frame. Once the geometry is computed, the next big block handles the animation. I create the figure, pre-create line objects for every link, and update their coordinates every frame. This makes the animation smooth and keeps MATLAB from redrawing everything from scratch. I also store the wiper tip positions every frame so that the swept region gets traced visually. The last section is the analysis part. Using the recorded motion, we compute the velocity, acceleration, angular velocities of the links, and an approximate motor torque based on a wiping force. Finally, we plot all of these characteristics. Now, let's run this code and see the animation. As we can see, the shortest link rotates completely, which allows the mechanism to sweep an area. Next, let's look at certain innovations which we have made on this mechanism. We have written a code for this as well. The main new thing in this code is that we didn't keep the wiper blade rigid like before. In reality, wiper blades bend when they press against the glass. So here we added a small model for that bending. The first few parts of this code are exactly the same, the animation. The only change is in the blade model. Basically, we take a wiping force and different stiffness values, stiff blade, medium blade, soft blade, and then show how much the blade would deflect. A softer blade bends more, a stiffer one bends less. Because of that bending, the tip of the blade doesn't follow the exact same path anymore. And since the bending also affects how hard the motor has to work, we also approximate and plot the torque for each stiffness. So overall, the innovation is we go from just animating the mechanism to also comparing how different blade stiffnesses change the swept area and the overall motor load. Now if we go back to the slide, the first adjustment as we can see is fairly obvious. That is to change the crank length O2A to increase the area which is swept. For O2A equal to 20, the area swept is lesser, whereas for O2A equal to 30, we can see that the y coordinate is lower for the higher crank length, because of which the area swept can be increased. This is the first adjustment which we can make.
My name is Javeer. Now, let's look at the second adjustment we made, which is spring-mounted blade, which replicates real wiper systems. A rigid mounting would cause uneven pressure and poor contact on a curved windshield. To fix this, we modeled the blade with a spring of stiffness K, and after testing different values, K equals 5 gave the best performance. This compliance helps absorb shocks at the reversal points, which are usually the most stressful positions for the mechanism. The motion becomes smoother, and more importantly, the torque spikes significantly reduce, lowering the load on the motor. The only trade-off is a slight reduction in wiping pressure if the spring is too soft, so stiffness selection must be balanced. This is visible in this graph. Moving on, let's look at the torque requirements for the motor. The required torque depends mainly on four factors: link inertia, joint friction, aerodynamic drag, and the spring's restoring force. From the torque curve, the highest torque demand occurs at the reversal positions, where acceleration rapidly changes. For real-world usage, the motor must be designed for peak torque, not the average. This ensures the wiper performs reliably during heavy rain, high friction, or when debris increases the load. Using lightweight links, good lubrication, and optimized blade geometry further reduces the torque requirement. Now, let's look at alternate wiper systems. First off, we have pantograph systems which are used in buses and trains to cover large rectangular windshields. Dual arm systems are common in larger cars for wider coverage, and single blade variable sweep systems appear in premium vehicles for aesthetic and aerodynamic advantages. These alternatives highlight how different vehicles require different designs, but for compact windshield shields, the 4-bar crank rocker we analyzed remains the most effective and simplest solution. That was our project. Thank you very much.